Good afternoon and welcome to one and all present here. I would like to thank Mr. Wasim and Mr. Karan for joining us for today for this session. I would also like to thank Mouser Electronics for giving us this opportunity of conducting a tech talk with analog device. So I would like to welcome the participants also for being present over here for this tech talk present over here for today. Before I hand over the floor to Mr. Wasim, I would like to speak few words about him. Mr. Wasim has 17 years of experience in design and development of industrial products with added expertise on functional safety. He works as product applications manager for precision converters and analog devices since 2015. He has completed his Bachelor's of Engineering Electronics and Telecommunications from Pune University. Today, Mr. Wasim will be covering a topic on analog to digital converter basics and technologies, and precision technology and analog devices, tools and roadmap. Over to you, Mr. Wasim. Thank you for joining us today.
Thanks, Bhavani. I hope I'm audible and my slides are up there.
Yeah, you're audible. Yeah.
Yeah. So firstly, thanks to DERBI for having me talk at this topic on data conversion fundamentals and new trends that we have at ADI. As Bhavani mentioned, I'm Wasim. I'm a product applications manager for the Precision Converter Group in analog devices. And my today's talk is all going to be about data converters, right? Primarily ADCs or analog to digital converters, right? What are the challenges that crop up because of this conversion? And what are the new trends? Then what are the architectures and what are the tools? I'll be briefly touching upon all of them. Okay, so let's get started, right? So our agenda for today, as I said, right, is going to be data converters. Although my primary focus is going to be only ADCs, but I'll just touch up upon ADC as well as DACs. The fundamental challenges, the things like sampling, quantization. I would touch upon AC and DC specifications of an ADC, what really matters, while choosing any ADC for any particular application. We will look into the basic or popular two architectures, right? The successive approximation register ADCs and the sigma delta ADCs. I will then talk about some new technology trends at ADI, some new tangents on integration, as well as some new tangents on architecture, right? And lastly, I would like to wind up with tools. These are important in order to make sure that, your rapid prototyping goes up very fast, okay? And you don't really have to wait for the actual silicon in order to do any kind of feasibility or getting your management on board with your concept, right? Okay, so first, what are data converters, right? So the real world problem, right, consists of taking a continuous signal, which is analog in nature, meaning it is continuous in time as well as it is continuous in its amplitude, right? And then applying distance by means of digital signal processing to the signal. Now we see that we have a variety of sensors like strain, temperature, right, current, voltage, right, many of them, vibration, things like that. Now these all give parameters in analog voltages that vary with time, as shown in the diagram above. Now this is something which is not understood by our controller or DSP, right? So what we need is a ADC to kind of convert this signal into a digital data, right? Now the resulting digital representation or codes can be processed to extract information content within that signal. It's fascinating to see the power of digitization, right? As we see so much information extracted out of these sensors. We all wear, wearable smartwatches, be it Apple series or, the MI bands or, Fitbits and all. And just by some few vital sensors, right, there's so much of information you can extract out of them. It's really fascinating. And it does open up, a big opening for a lot of more applications and data, right? So essentially, your ADC would give it to the DSP and then that would kind of extract the information. And as you see there, the ADC kind of converts the signal into a discrete signal, which is discrete in time, as well as it is discrete in its amplitude, right? The DAC is the other form, right, wherein this discrete signal is converted again back into continuous signal to take some actions, for example, something like a motor control or a pulse width modulated output, right, which is exactly the opposite form of it. Okay, so having understood where the ADC and DAC primarily falls in, let's jump into the fundamentals and challenges for an ADC, right? So ADC, as I mentioned, it's basically analog to digital conversion that basically involves two steps of sampling and quantization, right? Now, this conversion is essentially representing a continuous time domain signal, into a signal which is discrete, right, at uniform intervals, right? If you see over here, the top diagram, right, that depicts the sampling phenomena, the first one, right? So we have something like a switched capacitor input that would kind of sample and hold the value. And then it would be further quantized or rounded off, to a nearest value, depending upon the quantizer that you choose, right? So the continuous signal is first sampled discretely at TS, 2TS, 3TS. These are basically the sampling intervals, right? And then this value is kind of rounded off to a nearest digital codes like 101110, right? This, which is very well understood by a DSP controller or microcontroller or processor. So these are primarily the two steps. Now, what happens if the sampling speed is low, right? Like I showed you the TS value, if it's very low, if your sampling speed is low, this is the first challenge that we face in the ADC, and this is called as aliasing, right? Now, the best way to kind of understand practically what aliasing is the wagon wheel effect. Now, human eyes are a sampling system, and the brain then perceives the motion, right? All of us would have observed a spinning wheel of a car or truck on the road, and it's always perceived as slow moving, although the wheel is spinning at a much higher rate. This effect is called as aliasing, right? At times you'll think that it is going slow. At times you'll think, okay, it is going the other way around, right? So although the wheel is spinning at a faster rate in a known direction, right, your perception would make you think, the otherwise on direction or on the speed. This effect is called as aliasing, right? So let's again dive into further and understand, what really it is. Okay. So aliasing, as I showed you the spinning wheel example over here, right? Let's take, the spinning wheel in case one, okay? T0, T1, and T2 are like sample points. So you could just imagine that you're observing a wheel, right? At T0, you just open your eye and you note the wheel position. Then again, you close your eyes, and at T1, again, you notice, and at T2, again, you observe the value, right? Now, in case of a normal speed of a, of this wheel, which is spinning primarily in anti-clockwise direction, right? You will first observe it is at, say, 0, then it would have moved by, say, 1/3, and then again 1/3 at T2, right? So in this case, you can say, okay, well, hey, what I perceive is that my wheel is rotating in an anti-clockwise direction, right, at a particular speed. Now, I'll take case 2, wherein the spinning of the wheel is fast, right? But my sampling instance T0, T1, T2 are same, okay? Here, what will happen is at T1, the wheel would have rotated 2/3 of a cycle, and at T2, it would have rotated one full cycle and another 1/3, since it is spinning fast. Now, if I observe this closely, right, what I will think is that wheel is spinning in a clockwise direction, right? I'll see here, okay, this is 1, this is 2, and this is 3, which is not the case, right? And lastly, when it is very high speed, right, meaning at the first shot, it goes by one complete cycle and then another 1/3, right? At T1, you will still think that it is very similar to your first case, right? So these are the different perceptions that would come out of your sampling speed, right? So what is needed? We need to basically observe the wheel once every 180 degrees or once every half cycle, which we do in case 1. And that's how we kind of perceive the correct direction as well as the correct speed. Now this, if we translate to a frequency domain, this would tell us that, hey, look, you need to sample it 2 times by the time it completes 1 rotation. Or in other words, we need to sample it at twice the frequency of rotation. This is called something, this is called as the Shannon-Nyquist sampling theorem, right? You would have all studied this, wherein in order to sample something correctly, we have to always make sure that our sampling frequency is greater than twice of the maximum input frequency, right? So I hope this is clear. And now I'll just kind of move on to the electrical part of it. Now, a spinning wheel is always very similar to a periodic sine wave signal, as we see over here, right? It can be more mathematically formulated with the sine formula. So if we take the case one, right, and if we just create the time domain diagram of that, which is shown by this blue lights. Now this is a frequency of 1 kilohertz signal, right? And what if I sample it at 3 kilo samples per second, meaning 3 times in every cycle? So you will see this red colored dots over here, okay? And when I join them together, you will see that, okay, you're able to reconstruct a 1 kilohertz signal, right? So when we look at the frequency domain, you would rightly see that, hey, there's a 1 kilohertz signal there in the frequency spectrum, and you have your sampling frequency at 3 kilohertz. Now, this is in our first case of normal speed, so all things are fine and the signal can be reconstructed correctly. So what happens in the second case when the speed is higher? Okay, yeah, sorry. Okay, so what happens if my speed is higher, right? If I take a signal of 2 kilohertz and if I try to sample it, right, you would see this red dots again appearing here. But when we join them, you will still see a 1 kilohertz signal. Although the frequency of the signal is 2 kilohertz, since our sampling speed is not that fast, this tone is aliasing back and appearing as a slow moving signal of 1 kilohertz. This is called something like aliasing in the signal. And what we have to make sure is that we have to always band limit our input signal to meet Nyquist. And we have to make sure that our sampling frequency is always greater than twice of the maximum input frequency. Now, we could always say that, hey, my information is always going to be at 1 kilohertz, right? But you have noise, you have several other disturbances along the wires that could cause a high frequency signal in your inputs, right? And what will happen is this would cause aliasing back. So the best way to do it is to band limit the input signal with using a low pass filter. Okay. Now I hope this is clear. If there are any questions, we could take it at the end, right? So let's move on to the next process or the next step of quantization. Okay, so what is quantization? Quantization process is the representation of the magnitude in code form, right, of a continuous analog signal. The number of bits in the quantization process determines the number of discrete levels, and therefore it determines the smallest resolvable signal over here. So if you see the diagram here, what I'm showing you, it's like a 2-bit ADC, right, which would give an output of 0, 0, 0, 1 and 1, 0. So the discrete values are rounded off to a close values to the digital output codes depending upon the amplitude, right? Now, if you look at this center over here, right, wherein we see this 1 LSB, right? Now, when your analog input signal is varying in this range, the digital code is always going to be 1, 0, right? This range, right, which will give the same digital output code is called as quantization error or quantization noise, right? And the higher is this, the higher the resolution, right, lesser will be this quantization noise, right? So to explain it further, right, if you look at a 3-bit ADC, if we draw the input signal against the output, the codes that we plot over here, we could see a quantization error in form of this sawtooth waveform that we see over here. So this is maximum, at these endpoints over here and here, and it is 0, right, at the middle points exactly. Okay, so this is always tied to about 1 LSB, right, the quantization error. And as the input voltage increases, and if the digital code remains constant, this is the quantization noise that we see over here. Okay, now this is a standard ideal, ADC transfer function that we see over here. wherein the input signal varies the output code. And this is like a really ideal ADC that we see here. Okay. Further, this table shows a relationship between your analog input range or the full scale range and the LSB of different resolutions. So if you observe over here, as we go higher in the number of bits or in the number of resolution bits, right, your LSB value is going to go on reducing, right, because you are going to have more number of levels over there. As a result, what is going to happen is that the dynamic range is going to increase. What is dynamic range? Is basically the smallest difference in the signal which can be detected by the ADC is called dynamic range. So higher is your resolution, higher is your dynamic range or the variety of signal that it could accept, right? Okay, so this was on the quantization and quantization error. Before we move on to the specifications, I thought it will be good to touch up on different type of analog input signal definitions which are fed to the ADC, right? Things like the first one over here is a unipolar single-ended signal. Basically, this means that it will never go negative, right? It will be always positive above zero, right? And it will be limited to the spans of 0 volt to plus full scale. Next is the unipolar differential analog input signal. In this case, the ADC has a positive and a negative analog input, Vin plus Vin minus. These inputs are driven by two equal signals which span from 0 to plus Fs and are exactly 180-degree out of the phase. This is like a differential signal altogether. The third diagram shows a bipolar single-ended analog input signal. The analog input is applied to Vin pin of the ADC and has an amplitude of plus minus Fs by 2 and is full scale by 2 and is centered around ground, right? And lastly, the pseudo differential, the bipolar fully differential, right? And the pseudo differential, wherein the negative end or the other end could be at a very fixed value, any fixed value above 0, right? So that is called as a pseudo differential input. Now, these are all the type of inputs that would be given to ADC, and we need to really see our sensor as to what type of output it is giving, and then how do we translate it to our ADC. So ADC would have all these specifications as to what type of input it would be accepting, right? So most commonly is the first type, the unipolar single-ended input. So 0 to 5 volt standard or 0 to 3.3 volt, and then if the ADC doesn't accept this type of input, maybe you need to have something like a single-ended to differential converter using any op amp or diff amp, to make sure that the signal matching is done. All right, so let's move to the AC and DC specifications now of an ADC. It's important to understand these because every application will have a different demand, and based on this, we're going to choose what type of ADC and what application is very important to us. DC specifications are broadly like time domain heavy, right? Things like offset, things like how is the fidelity of the signal, the monotonicity, right? The how much is the signal changing? All these factors, these are DC. And AC specifications are more like whatever you see in a Fourier transform, right? Things like what is the harmonic distortion, harmonics, then my spurious free dynamic range. All these things are AC specifications. So ideally, you would expect the codes to be exactly 1 LSB apart, right? As we saw in the diagram earlier. So for an n-bit ADC, there would be like 2 raised to n codes, and we would expect all the codes to be away by 1 LSB. So if I go on slowly increasing my analog input, I should see that the transfer function should follow with that. And each step is kind of centered on an 1/8 of the full scale. If we take a 3-bit ADC over here. But then we know that life is not really ideal. So we do have errors creeping in, and these are very well justified with specifications like DNL, which is essentially differential nonlinearity. Essentially, it is the deviation of the actual code from the ideal 1 LSB code that I spoke earlier. So if you see at the diagram over here, the 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 black step waveform, okay, is the actual one. The dotted one is the ideal one. And you see at places it doesn't follow, right? Now this could be due to several reasons, okay, due to spurs, due to your code ineffectivity, like all those things. And this could lead to missing codes as well in your output. So it doesn't follow this thing. So this is the first one, which is called as differential nonlinearity. Right, we want to have this spec as low as possible, right, as this results in additive noise and spurs beyond the effects of quantization, right? So the next one is integrated nonlinearity, which is essentially, deviation of the code, actual code transition point from its ideal position on a straight line when it is drawn, between the endpoints of the transfer function. Uh, the best way is to kind of look at this diagram over here. So let's plot your input and your output together, right? And let's draw a line joining the endpoints. And then we look at how much is your deviation, right? With regards to my ideal ramp up, that is the INL or the linearity error that we see. There are two methods of measuring this, endpoint method and best straight line method. Mostly people do use the first endpoint method to measure INL. This again is a very important spec, as it really determines the fidelity of your conversion of the ADC. Okay, now we'll move to AC specifications. Like I mentioned, AC are mostly frequency domain parameters. So a time domain signal needs to be translated to a frequency domain signal, which is done by the fast Fourier transform that we see over here. So a time domain signal would look varying, sinusoidal wave. And say if we have 3 different frequencies as shown here, when we take a FFT transform and we try to observe this, you could see that, this is like something like a z-axis, right, that is shown to us. So on the x-axis of this guy is your frequency value, and this is the amplitude, right? And with this, we start doing the AC specifications, or the frequency domain centric specifications. These are basically, harmonic distortion, the total harmonic distortion, which is very crucial in audio and sonar type of application. Then signal to noise ratio, distortion, right? Then effective number of bits, then the bandwidth, as this is an frequency related spec, and of course, the two-tone distortion. Those are the main AC specifications over here. Just to really, talk about each of them, or some of them, or some of the important ones. SFDR is essentially the difference between your RMS power of your fundamentals frequency. Like if you are trying to observe a 1 kilohertz signal, right? What is the amplitude difference between the 1 kilohertz signal and the spur that you see in your noise floor, right? This determines your SFDR, which is spurious free dynamic range. Total harmonic distortion. This is again a linearity spec, right? And it is basically the root mean square of the first 5 or 6 harmonics that we see in your floor. And lastly, the SNR. This is basically a signal to noise ratio. This really determines your range of the ADC, and it's the most crucial spec while we talk about any ADC in a medium bandwidth or in an audio type of domain. A practical example over here that we show is the FFT plot, or a fast frequency transformation plot for one of the ADCs, right? So the x-axis is basically your frequency, y is your amplitude, and you can look at, say, SFDR is basically the difference from all the way from here to say here, right? So this color comes around little tad above 100, right? And then your harmonics would be basically this guy, and then the second, third harmonic, and the root mean square of that. So this is how potentially this would look like. In order to do this analysis, we would have an evaluation board, with an FFT analyzer algorithm. We would feed a very precise audio input or a signal input in order to make sure that we have very low noise in the signal itself. and then give this evaluation plots, for the customers for evaluation. All right, so we have kind of covered the AC and DC specifications. Now, before really going into ADC architectures, right, I would just say that every ADC has 4 types of inputs. It's not only your analog input that you're trying, which would be an input. There are other things like reference, right? Reference is something where your signal is always getting compared to and getting calculated. That's how the digital codes are kind of getting represented. The ground that comes along with reference as well as the power, then the supply power to the part, and lastly your input signal. So all these are inputs to your ADC, and we need to make sure that all of them are clean, right? To make sure that the ADC is performing as intended. All right. So let's jump into ADC architectures. We'll talk about 2 of them, right? The first is the SAR ADC, or the successive approximation ADC, which is one of the simplest architectures used, and it is the workhorse of A to D converters, or most popular one, we could say. It's very common type of converter, and it's used due to its precision and low cost. As can be seen, there are only 3 blocks which we see. Main blocks, which is basically your comparator, a register, a successive approximation register, and a DAC, right? The way it works is that on each clock cycle, the SAR register tests 1 bit at a time, starting from the MSB. For example, it sets the MSB high, okay, and what it would try to do, and all the other bits 0. Then the DAC outputs the analog equivalent, which is kind of mid-scale at the middle level, and then the comparator measures whether the analog input is below or above the DAC voltage. Now, if the output of the DAC is less than the input voltage, then the output of the comparator will be high, and MSB will still be kept at 1. And if it the other ways, the MSB would be reset to 0. This information gets stored in a register, and this value is maintained for the MSB of the DAC for the rest of the routine. And then on the next clock, the DAC output will be either set to 1/4 or 3/4. Earlier it was half, now it's 1/4 or 3/4. Depend, on the full scale, depending on the MSB. It does this repeatedly until all the bits are resolved, right? So if you note, this ADC architecture requires a held DC voltage over here that we see in the block SHA, as is known over there, right? Which is the, so you can imagine that this type of architecture, the main disadvantage being that the sample rate is depending upon the resolution. Because if you have more number of comparisons to do, more number of resolution, it's going to be more time consuming for us to do it, right? And yeah, so I think those are the key points over there, just to kind of, summarize, how this basically works. Further explanation is kind of, presented over here, like, yeah, so 0 off, okay. Right. So going further, if I have to take an example, say if your analog input is 6.428 and if your reference is say 10 volt, right? Here is a comparison, right? So your 10 volt, your 6.428 gets compared with half of your reference, that is 5, right? And then if it is yes, a 1 would be loaded into a register, and it will move to the next step, and then to be compared with 2.5, then 1.25 and 0.625, and that's how it goes on loading this successive approximation register with the value. Now, if you see, the more the number of resolution, the more the number of bits, the more time taxing it is going to be, right? So if we go to the advantages, it would be definitely low power, high resolutions, you can do it again at that cost of the time. Then small die area, low cost. The trade-offs are again noise at speed, right? What is the speed you want? How many number of bits you want? At the output at what speed is something that is a required trade-off there. Typical applications are, it finds it into instrumentation, industrial control, any form of data acquisition. Most of your motor control applications or basic 8-bit, 10-bit, 12-bit are mostly this SAR type of ADCs that you find. These are also very well integrated inside a lot of your microcontrollers that you would observe, which are available in the market. A particular example I would like to highlight from the SAR architecture is one's motor control part, the 7380, which is a very small package part, which released about 2-3 years back. The main specifications over here, are the SNR, the INL, DNL, and the total harmonic distortion. And it does find a lot of application, in motor control, sonar, power quality, and data acquisition systems. It has a nice range of about 1.6 to 3.6 to make sure a lot of your battery operated applications are also kind of taken care with this particular family. Okay, so the next architecture is basically a sigma delta architecture. Now in this, the key concepts are very simple for this particular type of ADC, although the maths is a little complex. I would just like you to maybe just focus the attention on the key concepts that I would kind of try to explain over here. So in delta modulation or sigma delta modulation, the analog signal is kind of quantized by 1-bit ADC, a comparator as shown. The comparator output is converted back into an analog signal with a kind of 1-bit DAC over here, right? And then after passing through the integrator, it is again kind of compared at the clock. So the shape of the analog signal is transmitted as follows. A 1 basically indicates a positive excursion has occurred in your last sample, and a 0 indicates that a negative excursion has happened. So the output of a sigma delta is more like a bit stream, right? So if the input doesn't change, right, the bit stream would be alternating ones and zeros, 0, 1, 0, 1, 0, 1, right? If it is going on increasing, right, then it may be a set of high, high, high. Okay, that would be the bit stream. If it's going low, it's going to be the other way. So if you look at how it is following, this red is your input signal, and this is how your bit stream is trying to follow up with the input signal, right? Here, what we do in the sigma delta ADC is we sample it at much faster rate than Nyquist, okay, to make sure that these conversions are very, very fast. And then we also have concepts of noise shaping and oversampling and spreading the quantization noise that I would just quickly talk about in the next slide over here. So the first concept is basically the sampling, right? Now we know that in Nyquist we need to follow, wherein your sampling frequency is twice of your input frequency. That would put the quantization noise at a particular value. As you see in this diagram, it's a little tad high over here, right? So what we do, we basically sample it at a very high rate, right? And what this does is that the quantization noise which was seen from 0 to half of the sampling frequency is spread across, and the spreading also reduces the amplitude, right? So oversampling and then spreads the noise. Then the digital filter we could use. Digital filter is something like a more commonly a low pass filter, right, that we could have at the output, and the black line that you see over here, and basically just cut off this removed noise from this entire signal. So you spread the noise and then you cut off from wherever your signal band of interest is, right? And then the third concept is basically on noise shaping, right? So the integrator that you saw in the earlier diagram would push this noise further out, right? And it would show an integrator type of shape. Okay, this would again help to reduce the quantization noise in band. Okay, and the digital filter then would knock off this complete range of noise, right? If you look at the math of it, it's pretty taxing, but I think the concepts are simple. So as long as we get the concept right, I think we would be able to follow what this is. All right. So sigma delta ADCs has some of the advantages, right? High resolutions, right? Unlike the SAR, right? We don't go through comparisons at each every time. We generate a bit stream that is at a very high frequency, and then with an averaging filter or digital filter, we kind of go on accumulating them. So this does help us to beat out high resolutions and high accuracy, from the bit stream. That again results in excellent DNL and INL performance. The noise shaping capability helps us to really push our dynamic range limits. And since it is just one comparator, this could be a low cost solution, and can be very much implemented on what is primarily a kind of a digital process, the filtering piece of it. The trade-offs is limited input bandwidth. Like if I kind of go back to the earlier one, right? Your sampling frequency is much at a higher rate, okay, and your input bandwidth is much lower, right? So your speed is obviously going to be very slow for the amount of sampling speed that you're going to have, right? So this really puts a limit on the input bandwidth, which again, does, because of which we are able to do slower sampling rates with this type of architecture. Although with some new advances in technology, we are able to hit 1 MSPS or 1.5 MSPS as well in sigma delta converters that I'll talk in the later section. Typical applications, right, because of the high dynamic range, the precision data acquisition and measurement and medical instrumentation, wherein you really need a very high amount of dynamic range to even, capture that very small, the blood level in the signal or the blood spike in the signal, or it could be any type of heart rate or any kind of abnormality that could be there, whenever you do any kind of ECG or EEG type of applications. So it does find a lot in medical instrumentation type of applications. Okay, here is an example of a sigma delta ADC, the AD7124, which is a 8-channel or a quad channel offering that we have. As you see, the sampling speeds are very low here, right? You see that we could do from 1.17 samples to maybe 19.2K boards, right? And but the advantage is that we get very up to 22 noise-free bits, like it's like a very high resolution that we get. The added advantage it does enable is we have got a complete signal chain integrated. So if you look at an application, you could just probably connect a sensor over here, and you should be done with your complete measurement. It does offer a lot of diagnostics, right, which aid cell level applications or function safety applications, and this is very much appreciated by a lot of customers as their overall journey of achieving cell certification is very much simplified by the amount of diagnosis that we have in the part. The part can do 2.7 to 3.6, so a lot of battery type of applications also can be solved with this particular ADC, and it does support the popular interface of SPI, with which you can probably have any microcontroller talk to it. Okay. So this is one of the applications examples of the SEN124. I've taken up a very common temperature measurement RTD type of application. So if you look at the diagram over here, we just have the ADC, and then with some biasing, with some low pass filtering, we could just directly connect the thermocouple or the RTDC or compensation, right, directly to your input signal. Okay. So with this, we do a lot of highest level of signal chain integration for a system on chip. We do save a lot of amount of space while we're doing it. So the complete integration of the analog front end is something that is very much appreciated, for these type of applications. Okay, so I have completed, the two main architectures, and now I would move on to some new technology trends at ADI that we have been doing and releasing over the past few years. I would take up two tangents, as I call it. The first is kind of integration, right? In terms of integration, how are we going there, right? So we have started something like a micro module, right, which is a kind of a complete data acquisition system that is housed on a very small single package, right? So if you look at this diagram over here, the right is the ADC, then you have a driver, you have all this low pass filtering to make sure aliasing is not there. And then you have a front end PGIA or an instrumentation amplifier to kind of make sure that the sensor sits well over there, right? So this entire area, if you see on a PCB, right, that is moved on to a die, right? Single die, right? There are multiple dies in this single chip over here. And then the space that we look at over here is almost like 10 times board reduction. So this small chip over here It has a fourth order anti-aliasing filter to make sure you don't have aliasing, a driver, then a 24-bit ADC there, and a lot of other power components and some critical passive components that are available on the branch on this die. The main advantage of this is that you get complete signal chain performance, right? That is guaranteed, right, by ADI. So we would have we would have the complete signal chain integrated on a single package, and all the performance metrics are guaranteed in the datasheet itself. So it would look something similar over here, right? As you see, it's called the ADAQ7768-1, which is one of the micro modules that we have released recently. And as you see over here, right, there are all these different sections or dies, right, integrated onto one single chip with the BGA package. So all this signal chain is integrated, and all you need is just to wire up the sensor, and all the specifications are kind of guaranteed by on the datasheet, by this part. This is again, in terms of integration, it's a very good progress that's happening, right? As the space saving is huge, and even a lot of the design work is taken by us as well, right? Because we don't want the designers to kind of spend their time in designing the PGIA or a low pass filter or anything like that. So entire thing is taken care by the single system on chip. It does also, significantly reduce the time to market for our end customers, development costs, and even the bill of materials is very simplified. So, later on, if you have an obsolescence issue with any particular capacitor, right, you don't need to worry because all these things are integrated inside. So as long as you have the part, your BOM or the inventory management is much more eased, with these micro modules. Right. So the second type of tangent, as I would call it, or new trend in at ADI that we are taking is even in terms of architecture, right? Solving problems inherently using some of our newer architectures, right? So that one of them is the continuous time sigma delta architectures that we are getting in for on some of our ADCs. The main difference with regards to the sigma delta ADC that I spoke earlier is that the sampling hold and sample and hold circuit, which is there, which is a switch capacitor type of input, is moved at a later on stage inside, right? So any input that is there or any sensor that is there would not see the sample and hold circuit at the start. It would see an integrator, and your sampling and hold is happening very close inside your quantizer, right? So what this helps us is in two terms. Firstly, your input drive is eased because your input is now resistive. You're just driving an integrator, because of which your drive requirements are eased. When we try to drive switch capacitor in this first case, right, we have to make sure this capacitor is charged and discharged within the proper times. Now that all is gone because we are just driving it with we are driving a resistor, and as long as the supply current is supported, we don't really need to worry about the dynamic switching characteristics of the input. That is eased. The second thing is this is alias free, right? So what is happening is, since your error or that is happening, right, the sample and hold is moved completely inside, right? Your aliasing is kind of getting integrated over here itself. So whatever errors you see because of aliasing gets cancelled in this loop itself, because the aliasing phenomena is now a part of this loop. In the earlier case, it used to happen over here. That's why we used to have low pass filtering to make sure and follow Nyquist as well. But here in this case, the aliasing by itself won't be there, since the error is much moved at a later stage inside the quantizer. Now, this is how we are trying to solve these problems that we see in terms of sampling, by getting into new architectures for precision, like the continuous time sigma delta. This allows us to even remove a lot of components in the signal chain, the driver amplifier, the low pass filtering components, the reference buffers, and maybe very much simplify the signal chain, right? Because since removal of all these components, if you take a single channel, these many amount of components you're reducing, and that much amount of reliability you're adding to the product, and you're also easing and simplifying the overall BOM management for the signal chain. Right. So with this, I complete the new trends that I spoke about, which we are kind of working in India. The next thing is tools, right? Um, we have a different set of online tools that are available at this website that you see over here, which kind of helps you in your prototype journey, right? Right from designing analog filters with the analog filter tool, or an enamp tool, which basically would tell you, okay, what are your supplies needed in order to make sure that you accept this type of inputs or this level of inputs. Then a photodiode application, which is very crucial for whenever you're measuring any type of blood related parameter. You pass it via transimpedance amplifier and try to measure that very low current input, right, with regards to that. The likes of SpO2 meter, or other photodiode type of applications would be used here. So then you have the DAC driver, which would basically tell you what post circuits you need to have in order to make sure that your circuits are driven correctly. We have the ADC driver tool, which would help you to play around with the different choices of fully differential amplifiers at the front end, and make the correct choices. We do have the DDS source generator and the virtual eval to do a virtual evaluation of the ADCs, rather than really waiting for an eval board to come. So these are all different type of tools that we have. I would recommend all of you to maybe have a look at these. Right, these are available at Precision Studio link, and I would certainly say that these are very helpful and does enable rapid prototyping of your design. With this, I end my presentation. I hope it was informative. You were able to at least maybe grab a few concepts here. In case of any questions, I can take it on later on once Karan completes his talk. Okay.
Thank you, Mr. Wasim. Thank you so much. Yeah, thank you, Mr. Wasim. Thank you so much. Now I would like to move on to the next talk what we are having. So I would like to introduce Mr. Karan. Mr. Karan is an application engineer at Analog Device, where he is responsible for providing technical design support to strategic and key customers focused on industrial applications like energy, monitoring, sensor interfaces, and data centers. Over to you, Mr. Karan.
Thanks. Hope you're able to hear me clearly, and
we're able to hear you. The screen is also visible, Mr. Karan.
Sure, thanks. So good afternoon, everyone. Thanks for joining this session. Today, my name is Karan. I work as a field applications engineer with Analog Devices. It's been close to 10 years working with ADI, and I mostly take care of the support for industrial customers, mainly revolving around the hardware part. Today, I would like to, since we have lesser time, I just have about 15 to 18 minutes to present. I would like to give you an overview about what ADI has to offer when it comes to healthcare, vital signs monitoring, what all solutions we have, and where we differentiate from other solutions available in the market. So it will be a very high level overview of a typical a signal chain and the kind of parts ADI has. I'll try to wrap up within 18 minutes, and just to give you a brief and a glimpse of what kind of solutions you can expect from ADI, and eventually you use it in your end applications to have a better product which you're trying to design. So when we talk about VSM platforms, there are different areas where the sensing goes in, mainly starting from the wrist or hand, where we see, as Wasim mentioned in the start of his talk, You have lots of variables which are moving from a typical health applications and more towards the clinical side of applications. We have products which go into those wrist-based sensors, mainly the fitness bands, the watches, or any other type of industrial equipment which goes into a typical wrist application, where the idea is to monitor the PPG, ECGs, the impedance for the skin, etc., etc., and also the temperature. Other area like we highlighted here is the finger, which is a pretty standard like sensing area where we have typically a finger clip. It could be a multi-wavelength clip or a single wavelength clip to monitor again the SpO2 levels and many other things like that. Third area is a typical area which is mentioned as patch, or a area which kind of involves multi-parameter electrodes. It can be in form of a patch, or it can be a typical electrode based arrangement. So ADI has solutions for that kind of sensing as well. And the latest and the last, which I think which is sort of becoming a relatively newer trend, is the hearables, where we have worked with many customers which do in-ear PPG monitoring. It's like a earpiece which goes into your ears and uh, does PPG and many other like artifacts related things. So we have like sensors getting into that area as well. This slide I have put just to show one of the platforms which ADI has developed. It is not a product, it is more of a open platform which we have tried to like develop. The idea is to put together all the available sensors ADI has, and uh, yeah, so the idea is to like put together all the sensors into a platform which looks more like a product, to see the capabilities of each of these sensors and how they perform in real life. So if you have heard of ADI before, we are mainly an analog company which mainly deals with the analog front ends, sensors, or the kind of solutions which we, if we put it together, forms a solution. But now with the new ADI and like I would say last 3 years, we have worked a lot, and we are happy to say that we are also looking into more of a solution approach, which would involve all the sensors, front end, computations, and eventually giving you a complete signal chain which has all the hardware blocks and also a algorithm or a specific ASSP kind of block also is available. So this watch involves many sensors, starting from the PPG optical sensors, along with a MEMS based accelerometer. Like both of them put together would form a sensor which does the heart rate and the heart rate variability along with the pulse oximetry. The accelerometer is used for two aspects. One is for obviously the motion detection, step counting, and also to remove the artifacts when the the person who is wearing the sensor is moving. So the heart rate should come accurately. So it is the sensor or the accelerometer is used for that purpose as well. We also have a impedance sensor. We call it uh, the AD5940 based impedance front ends, which kind of monitors the skin impedance. A temperature sensor, ADT is 7422 or 7420, which is a fairly accurate digital temperature sensor, uh, and like all of these parts, like if you look at ADI solutions versus other solutions available in the market, there'll be like two aspects where we usually focus on. One is on the low power operation, since these devices go into uh, uh, the end applications which are powered by battery. The quiescent current or the operating current for each of these devices is very important. So to increase the battery life and overall deliver a better product, uh, these smaller sensors needs to be very low power, and delivering a low power product with a same level of accuracies and the low noise is the key. So like just to give you an example of a temperature sensor here, it's ADT 7422. It is fairly accurate to up to 0.1 degree C in the band of, let's say, 25 C to 50 degree C. And even if you take the wider temperature range from like -20 to 105, or typical industrial temperature range, this sensor would still give you 0.25 degree C of accuracy. This is just one example. Uh, like this is a more elaborative explanation of what all blocks or what all sensors typically get into a vital signs monitoring application. And uh, we've also like put together certain parts which are like, I have shortlisted these parts specifically targeting like healthcare and VSM kind of applications. For example, the accelerometer you see here, the ADXL 362. This is a 3-axis, very low power MEMS based accelerometer. Like if I talk about power there, like in a typical like working or measurement mode, this guy would consume close to 1.8 microamperes of current in any output data rate. And like this also has many specific features for variables. For example, if you want to use this accelerometer as a wake on switch, so it has an option, we call it wake up mode, where you can use this device to use it as a switch to power off all the circuitry when the device is not used or kept aside somewhere. And whenever you see a movement on the variables, you can use this accelerometer. This accelerometer detects that and again powers up the remaining circuitry. This is one of the use cases. And in that mode, this device would consume around like 260 to 70 nanoamperes. And this is the I was calling the low power performance with respect to the noise performance of these accelerometers. Similarly, I just covered the ADT 7422, which is a temperature sensor. On the optical front end block, we have a module approach. For example, this ADPD 188 you see here. This is an optical module specifically designed for vital signs monitoring applications. This involves a photodiode, analog front end, and LEDs, multi LEDs for different wavelengths, all put together in a small package to get you the right optical processing for your application. Another area is the biopotential front end measurement, where we have parts like AD8233, which is like a very low noise, low power AFE. Again, the power consumption for this device is around like 45 to 50 microamperes, and delivering a common mode rejection ratio of close to 80 dB at 60 hertz with a 50 microampere of supply current is something we feel is a very important and a useful factor for these kind of applications. ADAS 1K, we call it. It has different variants to it. It's a multi-lead ECG front end, where especially for this 1K, you can connect up to six electrodes directly to this, and it has all the front end and the processing inbuilt into it. 5940 is the impedance front end, which monitors the impedance, and you can measure the skin impedance, or probably using the impedance and many other parameters do a health measurement or a stress measurement of the person. On the power side, we have ultra low power buck regulators, 53, 50, 60, 41, 24, which is a wireless lithium ion charger with it has a low power, low battery disconnect feature as well. So there are many parts going to like this power section. I have just put together few parts. All of these are very low power buck regulators, and this 53 series, it's like a PMIC, which has like multi voltage outputs, typically for these kind of applications. To kind of summarize on the parameters, or like when we talk about the overall solutions, we are not just talking about the sensors. We have actually worked on each of these parameters and the algorithms using our sensors to define what kind of accuracies you can achieve by using any of these sensors which are mentioned here. For example, for the activity monitoring, which is a step detection or a motion detection, uh, the MEMS-based accelerometer ADXL 362 is something which is a ultra low power part, very compact, and does many smart features like wake up mode, etc. For continuous heart rate monitoring, typically what we see as a case for the like you have these new applications which call for continuous heart rate monitoring, where all these photodiodes and LEDs are always on. So the power consumption along with the type of SNR, depending upon different types of skins being used, is very important. So the parts like ADPD, which 144 ADPD, the latest one is ADPD 4100, which has an even better SNR and a low power performance. So we are like improving. We are already into like fourth or fifth generation of all of these devices, and these are like more integrated devices, which is not just a photodiode or LED. It has everything. It has a photodiode, analog front end, and the LED all put together, say in a single package. It's like a module approach, which can be put together for your faster time to market kind of intentions. Similarly, for the body composition, the impedance front end, we have parts like AD5940, and if you need a MCU along with a 5940, we have a part like ADUCM 355, which which does impedance along with many other electrochemical measurements as well. So that's like Cortex M3 along with impedance sensors. We have that option as well. As I mentioned, like for stress monitoring, you can use 5940. On the power side, these PMICs, the LDOs, ADP16X, 5360. So all these are targeted for these low power and relatively higher accuracy applications. So also, like maybe I don't know, like some of you would be knowing ADI Maxim integrated is now part of analog devices, and I am happy to say that many like Maxim integrated as a company also was a very strong company when it comes to analog sensing, especially when we talk about healthcare and the kind of audience we have today. They would know Maxim used in very widely used in healthcare kind of applications. Since now Maxim is part of analog devices, there are very interesting platforms and solutions which you can directly pick it and use it for your requirement. Just to put together a few reference designs. This activity, I would say, was done by Maxim during the first wave of COVID. They quickly put together certain reference platforms which are targeted for these wearables and healthcare applications. involving a typical sensor platform where you can put in multiple sensors on a baseboard, uh, quickly test out your idea and get the data over a digital interface. Then you have certain reference designs which monitors the heart rate variability, heart rate monitoring, pulse oximetry, things like that. There are other like uh, platforms which Maxim tried to develop based on like health bands. Also for the ECG monitoring, a variable ECG and the evaluation platform is available from Maxim as well. Uh, there are few parts which are the star parts, I would say, which are being used in each of these vital signs monitoring applications. Uh, Mainly, if you see the Max 30XXX series, uh, the optical front ends, 30101, like are few parts which you can also look at. So like with ADI and Maxim, I would say like we have like from a sensor standpoint, we would have like almost all the front end interfaces on the power with Maxim and LTC, along with ADI's PMIC. So we have like a very wider and a dynamic portfolio of a low power operating PMICs and LDOs, and also like for your faster time to market, all these reference designs, the evaluation kits slash the watch is like available for you to look at and build your applications on and above what we have done so far. Thanks a lot. That was a like a short overview of what we have on the healthcare part. Maybe I think now we can take questions for the Wasim's talk and for this healthcare talk now. Over to you, Bhavani.
Thank you, Karan. Thank you so much. Thank you for your presentation. So now we're open for questions. Any questions, participants?
Karan, one question. This is Tony here. So, what is the evaluation module that typically that you recommend for some of these the vital parameter monitoring?
Yeah, Tony. So typically, what we call evaluation platform would involve a sensor interface where like we pick up any sensors. For example, ADAS 1K, which I just spoke about, which is a multi-lead ECG AFE. We'll have this AFE along with the MCU platform, which has a digital interface either connected to a PC or to a serial interface. The idea is to have those sensors or the electrode interface directly to this platform and get the data quickly on the PC or a serial platform. Like what we're trying to say is it is not a product, it is a relatively bigger board than an actual product, but you have like the front ends, the MCUs, and the digital interface all put together into a single baseboard, which would have like isolation and things like that as well.
Yeah, thanks. And one more question. If, yeah. So when you're going towards a module approach, even trying to integrate maybe even 60-70% ready, right? How does it look from conformance perspective, right? What work the startup has to do in terms of regulatory clearance? Is it totally on the startup, or even for example for SPO2? Some of the calibration curves are they built into the module, or it's something which has to be totally done by the startup itself?
Okay, so let me take this liberty to show you one slide. I think it is a backup slide for me. Maybe I think that would help how a typical module looks like. Like, are you able to like see my screen?
Yes, we can.
Okay, right. Yeah. So again, this block, which we call it as a module, uh, doesn't have any programmability features with respect to the algorithm as such. The block here would involve, like from if you start from the extreme left, you have these photo detectors, detector 1 and detector 2, which are the photodiodes, and then you have the processing, the analog processing for this, which is the transimpedance amplifier, filters, the integrators, getting into ADCs, like all of it put together, and finally eventually giving you a digitized information. So this module would not get involved in like any of the algorithm processing as such. It would only uh, kind of process the input signals very effectively with respect to the kind of SNRs we have in this product, like combining photodiodes and the receivers, whatever reflective wavelength we get, or the LED signal we get is processed in a very fine way to get you the accurate digitized information. Now that information is supposed to be used by the algorithm which the startup is going to develop. So that's the next block, which would be the MCU or a host processor, which takes this digitized information and applies it into their own algorithm. So like from ADI side, this would be our offering. What we have done is to right now we have like developed one algorithm which kind of shows the capability of like how these like sensors work in the actual world. We can like look into case to case basis, like on what portion can be like shared with the startups to like build their own algorithm on it. So in short, I would still say the onus on the algorithm relies on the end user. From ADI, we take care of the complete sensor signal conditioning. So
yeah, it is clear. Yeah.
Yeah, thanks.
Any other questions, participants? Thank you, Mr. Karan and Wasim, for organizing this and sharing your presentation to us. So can we have a quick pic so that if everybody can switch on your video, so we could click a pic. One minute. Thank you, everyone. Thank you so much. Thank you all. Thank you so much for joining. Thank you. I would thank even Mr. Wasim and Karan also. Thank you so much for being over here for this session. We would like to get connected or get connected for other sessions in future. Thank you so much.
Sure. Thanks.
Thanks, Awari.
Thank you, Mouser team. Thank you, Suman. Thank you, Avinash. Thanks a lot for joining.
Yeah, thanks Derby and thanks Analog Device. Thanks Karan and Wasim and also Sunil. See you. Bye.
Thank you, everyone. Thank you.
Bye.